Hello, welcome back. In this final video, we're going to be examining graphing motion. Graphing motion means we're going to be taking a look at three different types of graphs. Position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. Now, in this video, we're going to start with the first two. We will eventually start tackling acceleration time graphs, but don't worry, these are actually the easiest of the three. What we're going to do below is we're going to examine how do you find these particular things from various graphs. For instance, how do you find these things from a position time graph? How would you find these same things from a velocity time graph? Let's get into it, and then we'll put it into practice. Now, I'm going to add one more onto this right here, moving in the positive x direction. So when you're going in the positive x direction, your graph is going to tilt upward. It's going to go upward. It's going to be increasing slopes, right? So moving in the negative x direction would just be the opposite. You're going to tilt downward. For a position time graph specifically, okay, when you see constant speed in this or constant velocity, it's going to be a straight line, okay? For instance, kind of like this. If you saw a position versus time graph that looked like that, that would be a constant speed problem, okay? Or even like this, right? That would be a constant speed problem. Okay, how do we show speeding up? Well, to show speeding up, the curve, it's not a line anymore, it's a curve, goes from flat to steep slope. All right, let me show you a couple examples. Okay, one we could do is like this, where we are going like this, and you can see we start with a flat slope, and the slope is getting steeper as we go. Okay, the object's going faster. One of the things that we're going to learn shortly is that the slope of a position time graph is the velocity. Could also have something like this. Notice you're still going from a flat slope to a steep slope. So you're still speeding up, but you're speeding up going in a negative direction, as opposed to this being in a positive direction. Slowing down, it's just the opposite. Now the curve goes from steep to flat. Right? So that might look like a couple of these. Could go like that. That's showing you steep slope, but the slope is getting flatter over time, meaning the velocity is slowing down over time. Could look like this. Notice how we're starting steep. It's a negative steep, but it's still steep, and it's getting flatter over time. Okay, displacement. Displacement is going to be just your change in position. Change in your position x. So in other words, displacement is going to be final position minus initial position. Okay, average velocity, you can find that by just simply finding the slope of the line segment for that time interval. Now, what about a velocity versus time graph? Okay, well, here's one example right here, but there's many other ways we can draw a velocity time graph. So again, I'm going to start with moving in the positive x direction. So when we're moving in the positive x direction, a position time graph is tilted upward, okay? But moving in a positive x direction for a velocity time graph means the graph is above the t-axis. The t-axis is this right here. So if a graph was, for instance, if you had a graph looking like this, a velocity time graph looking like this, where it was upwards, okay, above the t-axis, you're moving in a forward direction, positive direction. Whereas this graph, you can see it's below the t-axis, right? That would be moving in the negative direction. Okay, now constant speed would be a flat line, a flat zero slope. So if I have a velocity versus time graph and I had something that looked like this segment right here would be constant speed. Speeding up is when your graph moves away from t-axis. Okay, so again, if I have a graph that looks like this, and I'm just kind of throwing a whole bunch of possibilities here. This part right here, where it's moving away from the t-axis, right? That would be speeding up. But you can also see you're moving away from the t-axis right here too, okay? Because we're going away from the t-axis to get to that time, and then away from the t-axis to get to that time. Okay, so whenever you move away from the t-axis, you're gonna speed up. Slow down is just the opposite. Graph moves toward the t-axis. Okay, so if I use the exact same graph from above, okay, we know these are constant velocity right there because they're flat lines. We know that these two segments are speeding up because they're going away from the t-axis, but these two, here you're approaching the t-axis and you're stopping, right? Velocity is 0 there. And here you're also approaching the t-axis. Those are instances where you are slowing down. So when the graph is approaching the t-axis as opposed to going away from the t-axis, you're slowing down, not speeding up. Displacement can be found by finding the area between the graph and the t-axis. Okay, so if I go back to that exact same graph, finding this area, right, would be a positive displacement because it's above the axis, and finding this area would be a negative displacement because it's below the t-axis. But anyway, finding the area between the graph and the t-axis will give you your displacement, how far you went in a particular direction. The average velocity would be the midpoint velocity, because this is a velocity time graph, so that's pretty easy. And to find acceleration, you find the slope of each segment, of each line segment. So now that we have some of this information available to us, let's go ahead and take a look at some examples. Follow me to the next page. Example 1. Use the graph below to answer the questions. The first thing you do when you encounter a graph is you annotate the graph for all parts of the motion, okay? So here's what I'm going to take a look at. Number 1, it's a position versus, well, it's always going to be time on the x-axis in seconds, but it's a position versus time graph. Now, what do I notice? I notice that we're starting from an initial position, right, at time equals 0, at negative 10 meters. So remember, the problem starts, x naught starts from 0 unless the problem says otherwise. This is one of those times where it says otherwise. And you can see it takes 4 seconds, and we're going at a constant speed, so this would be constant velocity because it's a straight line, to a position of 30. Then you can see right here, when you encounter no change in position for 2 seconds, you've stopped. So we've stopped. No change in position. Now finally, you're going from flat slope to steep slope. This means you are speeding up in a negative direction. So that's the first thing that you want to do, is you want to get a handle on what is actually going on in the motion, and then all of your math will then support that, okay? So part A, for which sections are the object at rest? Well, that's only going to be B. It's this part right here where you're not moving. For which sections is the object moving in a positive direction? Well, that would be the only part that has a positive slope. That would be A. Okay, which sections are the object accelerating? That's going to be the only one where you see a curve. That would be C. Because a curve indicates a change in velocity, a change in slope, thus a change in velocity. Therefore, that's the only time you're going to accelerate, is when you have a change in velocity. Now, for part D, E, F, and G, we're going to have to do some calculations here. So let's do that work down below. It says find the distance and displacement for each section of the trip. So for part D, okay, section A, we'll start with section A. Okay, what is the distance? Well, the distance, okay, is going to be, you're going from -10 to 30. So the distance is just going to be 40 meters. The displacement, however, is going to be a change in position, final position minus initial position, which would be 30, because that's where you end up, minus a -10. Notice that also gives you 40. Okay. Let me see here. Oh, we gotta do segment B. So segment B, you stay at 30, so you have no distance. Distance is 0. Displacement is 0. You don't move anywhere. And for segment C, okay, we're going from 30, it looks like, to -20. So the distance would be 50, because remember, distance is just total length traveled, right? But now displacement, right, we're going final minus initial position. So let's go -20 minus 30, and that would be equal to a -50, meaning we traveled 50 meters, but in a negative direction. A negative direction could be left, down, or backwards. Okay, there's part D. Part E, find the average velocity for each section. So average velocity is your displacement over time, over that time interval. So let's go section A. Our displacement was 40 meters, and the time was 4 seconds. So we're talking about an average of 10 meters per second. Okay, for segment B, our average velocity is 0, because you remember, you're not moving. If your displacement is 0, your average velocity is going to be 0. And then for part C, we're going to go displacement over time. Our displacement is -50 meters, and it took, let's see, from 4 to 10 seconds is 6 seconds, so that's a 6-second time interval. Please take a second to put that in your calculator. Wait, I'm sorry, that's a 4-second time interval. From 6 to 10 seconds is a 4-second time interval. We should be getting about -12.5 meters per second. Okay, again, what is the negative What does the negative signify? It means you're going in a negative direction. For instance, maybe you're going backward, or maybe you're going to the left, or maybe you're going down, but you're going in a negative direction with that particular velocity. All right, part F. Let's find the average velocity for the whole trip. So that means you're taking total displacement over total time. So my total change in position would be, my final position looks like it's negative 20. My initial position was negative 10, so negative 20, negative 10. So I'm going negative 20 minus a minus 10, which is the same thing as negative 20 plus 10, over the entire 10-second time interval, which would give me negative 10 over 10, or negative 1 meters per second squared. Meaning overall you're going at a speed of 1 meter per second if you averaged it out, but overall you're tending to go more to the negative direction than the positive direction, hence the negative in there. All right, and then finally we're going to make a velocity time graph for the motion. Now here's how we'll do that. Part G. We're gonna make a graph. Okay, and I need to segment it out. So 2, 4, 6, 8, 10 seconds, right? And then velocity is in meters per second. So I'm starting with an average velocity of how much? 10. So what I'm going to do is I'm going to kind of segment this out, maybe 5, 10, 15, 20, and then I'll do the same thing. Negative 5, negative 10, negative 15, negative 20. So for the first part of this trip, for first 4 seconds, I have an average speed of what? 10. Okay, then for the next part, I have no speed. So I'm going to make a flat line for a couple seconds down here. Okay, and then finally I have an average of negative 12.5 for the remaining 4 seconds. So I'm going to go down here. Right, and there's the rest of my graph. Okay, oh, I'm sorry, I can't make that constant. We're accelerating. I forgot. We're accelerating during that time, so I need to slope it away. So it should look like this until you get to about 12.5. Let me see, I should, there we go, about there. Example 2, let's take a look at the motion. Now we have a velocity time graph. Let's break down the motion, guys. So I'm gonna color code this and I'm gonna highlight different sections, okay? So in gray, this part, we're slowing down. We're slowing in the positive direction because it's above the t-axis, okay? Here, we're speeding up, but in the negative direction because it's below the t-axis. Right here, you stop. Exactly at 1 second, you stop to change directions. Okay, for this segment, right here, you're moving with constant velocity of 20, negative 20. The negative just means you're in the negative direction, right? But constant velocity of 20. And then here, in this final segment, right there, you're headed back towards the t-axis. So what are we doing? We're slowing, right? But in the negative direction. Now put all these together. If I'm slowing, which is a negative change in velocity, in a positive direction, that's negative constant acceleration for that time interval there. Here I am speeding, that's a positive change in velocity in the negative direction. That means I have also a negative constant acceleration. And finally, you can also tell it has the exact same slope the entire way. It has a negative slope, in fact. Here we have negative constant velocity because it's below the t-axis. And here, since we're slowing, which is a negative change in velocity, but in the negative direction, this is going to result in a positive constant acceleration. Think about it. It's a positive slope, right? That should make sense. So which sections are the graph accelerating? Well, that would be sections A, B, and D. Which sections are at rest? Only at, there's no section at rest, but specifically at t equals 1 second, that would be when you're at rest. That's the only time you're at rest in this graph. For which sections of the object moving at a constant speed? That would be C, right there, constant velocity. For which sections of the graph moving in a negative direction? Well, you're only moving in a negative direction for anything below the graph. So that would be B, C, and D. For which sections are the graph slowing down? When you're approaching the t-axis, that would be A and D. Okay, now let's find the acceleration for each part. We'll do our work down below. So for part F, to find the acceleration, that's the change in velocity over the time interval. So the change in velocity for the first segment A is going to be 0 minus 20 over a 1 second time interval, which is negative 20 meters per second squared. Okay, for B, that's for A. For B, we're going to go A equals, like we're going negative 20 minus 0, so negative 20 minus 0, over, again, another 20-second time interval, so that's also going to be negative 20 meters per second squared. And if you had simply just found the slope of that, you would have gotten the exact same thing. All right, the acceleration for C is going to be 0 because it's flat, there's no change in velocity. And for the last part in D, we have, let me see, we're ending at negative 10 right there, and you're starting at negative 20 over a 1 second time interval, which is a negative 30 meters per second squared. Sorry, minus a minus 10. Minus a minus 10 is plus, that would be a plus 10 meters per second squared. Okay, and then part G, we're going to find the displacement for each section. All right, so now to do that, we're going to find the various areas. So we're going to find this area here. We're going to find this area here, this one here, and then this one here. So we have 4 areas we need to find. Most of them are easy. Most of them are triangular or rectangular. This one here is trapezoidal. So I would urge you to break that up into a small triangle and a small rectangle. Okay, here we go. What is the area from 0 to 1 seconds? Well, it's 1 times 20 is 20. Take half, that would be 10 meters. Okay, and it's positive 10 meters because it's above the t-axis. Then we're going to go same area for this one. If you look at it, it's symmetrical. 1 times 20 is 20. Take half, it's 10. But since it's below the axis, this is going to be negative 10 meters. The square part from 2 to 3 seconds is 1 second times 20 is 20. But below the axis, below the t-axis, this would make it negative 20 meters. All right, and then we have 10 meters here, plus another 5 meters here. So a total of 15 meters there. So that's what we're finding. We're finding the area for each section. Okay, so for G, oops. Okay, for section A, we're going, right, base times height divided by 2. So 1 times 20 divided by 2, right, is positive 10 meters. For section B, it's, again, base times height divided by 2, so the area, the displacement, delta x, is going to be 1 second times negative 20 over 2, which would be negative 10 meters. Part Part C is the square. For that one, we're just going to go base times height. So that's going to be 1 times negative 20. Right, equals negative 20. Okay, and then lastly, part D, it's going to be 2 parts. So you've got the square, okay, which is base time, which is the rectangle, excuse me, base times height. So we're going to go 1 second times negative 10. That would be negative 10 meters. But then you also have this, which is 1 second times negative 10 divided by 2, which would, of course, be negative 5 meters. So delta x for this section would be negative 15 meters. Okay, the last thing we need to do is sketch a position time graph and acceleration time graph for this motion. All right, here we go. Now, what I'm going to do is I'm going to sketch the position time graph to the left here where we have room, okay? And I'm going to make it like this. So draw a sideways T, just like this. Use the same time intervals, 1 to 4 seconds. So here's 2, there's 1, there's 3, there's 4. 1, 2, 3, 4 seconds. So that's T in seconds. This is going to be X in meters. Okay, and I think we could probably label this maybe 10, 20, because I'm looking at this. My largest displacement seems to be, negative 20. So I think we can go probably up to 30. So 10, 20, 30, negative 10, negative 20, negative 30 on the x-axis right there. All right, here we go. So our first displacement, we're going to start at 0. Okay, I'm going to start at 0. And our first displacement is going to go 10 meters in 1 second. Okay, and we decelerate to get there. So we talked about this earlier. When we're slowing down, we are going to go from steep to flat. So we're going to make a dot at 10 meters. So this is 10. This is going to be 20. This is going to be 30. This is negative 10. This is negative 20. This is negative 30. So I'm going to make a dot at 10, right? But I need to go like this. I need to go steep to flat to get there. So there's the first part of the graph. Okay. Now the next part, we're speeding up, but we're going in the negative direction. We have the same 10-meter distance, but this time we're going flat to steep because we're speeding up. So the way we'll do that is we're just going to come right back down like that. Okay, and if you think about it, this area plus this area brings you back to 0, which is exactly where you started from originally. Okay, our next area is negative 20, so negative, and it's a constant velocity, so we're going to do a straight line to negative 20. So make a dot at negative 20, and to get there, we did a straight line. That's the constant velocity to it. And then the last part, we're going 15, okay, 15. Now, it's still negative, so it's still going to keep going down, and 15 more than negative 20 would be negative 35. So if this is negative 40, we're going to make a dot at negative 35. And keeping in mind, we're slowing down to do this. So when we slow down, we go from steep to flat. So it should go like that. Okay, and there's our position time graph. We will explore position time graphs and velocity and acceleration time graphs in much more detail. So remember, this is just to give you an introduction to those concepts, okay? So don't worry, we're going to dive into it and help us understand it a lot better. Now, on the right side, we're going to draw the acceleration time graph, and this is actually far easier than any of the other graphs because we're dealing with constant acceleration. And how do you draw anything that's constant? With horizontal lines. That's exactly what we're going to do. Now, our accelerations were all, we calculated them, they were all in the range of, looks like negative 20 was our largest. So same thing, we'll go 10, 20, and then down here, 0. This is acceleration in meters per second squared. This is going to be time in seconds. Again, there's 2, there's 1, there's 3, there's 4. Okay. For the first second, or the first 1 second time interval, it's -20. So here's -10, here's -20. So we're going to draw a line, a horizontal line right there at -20. Okay. Now for B, it's still at -20. Okay, and why is that? Because it's the exact same slope all the way down. Okay, now for part C, there's 0 slope because it's not going up or down. So we have this part here. 0 slope means 0 acceleration. You can leave this discontinuous. You do not need to connect those, okay? That's not necessary. We'll leave them discontinuous. And then our last one had a slope of +10. So we're up to +10 for our last one right there. And there's our acceleration time graph. Much easier to graph than position time graphs. Position time graphs, you have to cumulatively add the next displacement to the previous one to continue the graph moving forward. Acceleration time graphs will always be horizontal lines above the t-axis, on the t-axis, or below the t-axis. So they're incredibly easy to produce. I hope you found this video tutorial to be helpful. Again, remember, the point of the video notes is to give you an introduction to what we will do in class together. And I want you all to feel like you have a basic level background of where we will all head together, okay? We're going to do the hard stuff together in class. That would be the problem solving. But hopefully now you have some sense of where we will be going. Thank you, and see you next time.